Now, this is how the stress states are going to be at before cracking, and we have seen that the both principal compression and tension is going to be equal to the shear stress when the concrete is uncracked. The moment it cracks, you find that your principal stresses will become 2 tau, and then another one, because it is already cracked, it will become 0 because it is a cracked element. It will be subjected to only compression like this, right. So, you have cracked element like this. Now, let us see what is the web shear reinforcement rule. So, if you have to plot all these principal stress trajectories for an uniformly distributed load, you will find that the dashed lines, that what you see here, these are all compressive stress trajectories, and we have discussed that the crack will always be perpendicular to the tension. So, if I have to assume the crack, it will always be this dashed trajectories. This is what it is. So, the compressive stress trajectories are nothing but your crack lines, that you know. So, solid lines tells you tension trajectories, and typically the failure patterns for this, if you look at the cross section subjected to beam, subjected to point load like this, you get this kind of force distribution. And if I look at closely this crack, and you will find that, let us say I have some steel which is subjected to some additional tension at the crack location. In addition to that, if you have a stirrup, that will also be subjected to tension because it is bridging the crack. In addition to that, now I am going to have there is a strut that is forming between these cracks. Okay. So, the concrete strut will be formed. That strut is going to push it in compression. That way, in this zone, I will satisfy the equilibrium. If I take the free body diagram of this strut, that is for the concrete stimulated strut. So, there is always going to be close to that, between the cracks you will have concrete strut will be in compression, but then they will form like a truss, okay, strut and tie. So, basically the longitudinal bar and the stirrup will be in tension, and then the concrete between the cracks will be in compression. Okay. So, this is a diagonal failure mechanism. Now, how do we estimate the capacity for design purposes? So, the failure mechanisms in shear can be quite complex. So, but for us, to see design, we need to come up with some simplified ways of calculating the capacity. So, people have assumed this truss. They assumed that concrete, between the cracks will act like a strut, and the stirrups and rebar, the longitudinal bar will act like a tie. Okay. So, you see here, if I take this cracked element like this, and we assume that this crack angle is going to be, let us say, 45 degree, then this distance becomes d cot 45, from, if this distance is, let us say, equal to d from here to here. So, we know that this is equal to d cot 45, and if I take this stirrup to be at an angle alpha, I think this distance will become d cot alpha, and S1 will be the total distance over which all the stirrups from this stirrup, this stirrup, this stirrup, this stirrup, this stirrup, all of them will be intercepted by the crack. Whatever that stirrups that are being intercepted by the crack will be tension. That is what will be that tension resistance. So, how many number of stirrups that will be intercepting that crack? So, which will be basically S1 divided by the spacing. Okay, have, and this is your number of stirrups that are basically crossing this crack. Now that we have understood this diagonal shear tension mechanism, we know that we need to put some transverse reinforcement to enable that the truss mechanism is formed, right. So, from design point of view, we know that when we do the sectional design, the demand has to be made sure that the demand VU, that what we have, should be always, when it is becoming more than the concrete capacity, we end up putting some stirrups. Now, how much that quantum of shear resistance that should come from stirrups is the difference between the demand and the concrete shear capacity, and if you express in terms of stresses, you multiply by the area to get that the stirrup resistance required for additional shear which is not offered by the concrete. Now, this can be explained from a simple free body diagram. If I take a very generic arrangement like this, so you have a crack like this, it is going, and if I assume this crack to be at 45 degree, then if you take this distance as d, then you will find that this corresponding distance is also going to be d cot 45 because it is a 45 degree crack. Then in terms of reinforcement, if you put this reinforcement at a generic angle, let us say at alpha, if I do that, then how many number of stirrups that it will be crossing will be from d cot 45 plus, now there is one more stirrup also is crossing. So, if you take this angle as alpha, then this horizontal distance will become d cot alpha like what we have here. So, the number of stirrups that are within this distance S1 will be actually crossing that stirrup. So, that S1 then we know it is equal to d cot 45 plus d cot alpha, right. So, this is the number of stirrups that will be crossing within that distance a particular shear crack, right. Now, we know that the shear resistance is coming from tension contribution of the stirrup, and now that these stirrups are inclined at an angle alpha, the vertical component is going to be Ts into sin alpha, right. What is the maximum Ts that it can take? That depends upon, now if you see this shear crack is actually a through crack, it is actually a through crack. That means what is the meaning of a through crack? That from one front side, if I look at the crack, that will be this, the back side also will become visible. So, that means the crack will cut through whatever the number of stirrups that are there. So, if I put 2-legged stirrup, then both the legs will be effective. If I put 4 legs stirrup, then all the 4 legs will be effective in arresting that crack, right. So, now how much is the maximum that a stirrup can offer in tension? It will be area of that number of legs of the stirrup that are crossing multiplied by that Fy, okay. So, that is what we are taking ASV into Fy. So, ASV will be, let us say if you have 2 legs, it will be 2 into area of 1 leg, that is the ASV, and Fy is the yield strength of the steel, right. So, now if you look at it, number of stirrups that it is going to take, we have to take it, right. So, this is the Ts component. Now, what is the vertical shear contribution? It will be Ts into sin alpha, right. Now, we have to find out how many number of stirrups that are actually crossing the crack. That will come from S1 is the distance that we have taken, that divided by S. S is nothing but your spacing of this stirrup. So, S1 by S gives me the number of stirrups that are actually crossing this crack, which is we are taking it at 45 degree, right. So, S1 we have already calculated as d cot alpha plus d cot 45, and if you substitute that, then you will find that it is basically, now why this 0.87 comes? It is basically coming from partial safety factor, material factor for steel. We divide the Fy by 1.15, so you get 0.87. So, that is why instead of Fy we are taking the reduced strength, which is 0.87 Fy times ASV into sin alpha into d cot alpha plus cot 45 divided by SV, right. SV, here also we can say this as SV. SV stands for spacing of the stirrups, right. So, if you substitute that, then you will find that for generically this one it is, if I assume that stirrups to be at 90 degree, that means if they are going to be vertical stirrup, which is a more common, the common form of stirrups that we put. We always put the stirrups in the vertical direction, because when you have a load reversal, if the shear force direction is changing, then if you put exactly at one angle, it may not be effective. So, but if you put it vertical, even for any stress reversal, even if the shear force is changing direction, still there will be a component that will always help you in arresting that crack. So, that is the reason that more commonly we put vertical stirrups. So, if you substitute alpha equal to 90 degree, then you will find a very simplified expression for the contribution of stirrups in shear resistances 0.87 Fy times ASV into d by SV. Again, ASV stands for, if you know, number of legs multiplied by area of one leg of stirrup. Okay. So, if you have 2 legs, it is 2 into area of one leg, right. So, that is how we get this ASV. Okay. Now, one more thing that we talked about it in more circle is, you know, when you have combinations of normal stress and shear stress acting in an element, and when you convert it into principal tension and principal compression, concrete being weak in tension, it will always, the principal tensile stress will reach its maximum material strength, that is tensile strength. But if you apply lot of pre-stress, especially for a very thin members, then you may have a situation that before concrete reaches its tensile strength, the principal compressive stress can reach the compressive strength of the concrete, and that we should avoid. Why? Because whenever the concrete fails by principal compression or in compression, it is going to be a more brittle mode of failure. So, we can never have concrete failing in principal compression before it cracks and fails in some way in tension. Always we want concrete to crack and steel to yield before it can fail in compression, right. So, how does the code addresses this? Code is going to make sure that you are not going to have failure in compression by ensuring that the tau v, the nominal shear stress tau v, can never go more than tau c max. Okay. So, there is a maximum shear stress that is allowed in code. You can never have tau v going more than tau c max, that is given in this table 9 of IS 1343, that tells you for different grade of concrete what should be the tau c max, right. For example, for M30 it is 3.5, for M50 it is 4.6, M55 and above 4.8. It has been capped at 4.8 because we do not have a lot of data on high strength concrete, how much is the maximum shear stress that we can allow. So, that is why the code is capped at 4.8 megapascal. Again, this is what we said, you have principal tension and principal compression. Now, the sigma 1 can also reach F prime C, right. So, that it is not allowed, right. So, we do not want to have, due to shear, failure happening in shear compression mode, or in other words, the principal stress should not reach its maximum compressive strength and lead to failure in compression. So, that is the intention. Okay. So, this was we said, and we always, you know, there may be a situation that sigma 1 can become greater than F prime C, and this should not happen. Okay. We cannot allow this. Okay. Now, let us look at how the IS 1343 code provisions exist, and we know that always the ultimate shear resistance should be greater than the shear demand. So, this is the factored shear force at the cross section, and this is your demand, and this is your nominal shear strength, right. So, and the nominal shear strength comes from two contributions. One is from concrete contributions in shear resistance, that is Vs, and the stirrup contributions in shear resistance. Now, what is Vc? Now, we have looked at Vc, there are two equations that we had, right. What are those? So, concrete can either fail in diagonal web shear cracking, or it can fail in flexure shear cracking. And for this, we framed an expression for Vc naught, we call that as Vc naught. The next one we call them as VCR. So, right. So, that is why the code is saying there are two things that we take. This is your Vc naught, which is basically your diagonal web shear cracking, and this is your flexure shear resistance. We have previously discussed how these equations were derived, right. And please note that for a section that is already cracked in flexure, here there is no VP component, okay. The reason is because already the section is cracked in flexure, so the beneficial effects of VP is conservatively being not considered in the flexure shear resistance, it is only included in web shear resistance, right. So, these are the things. So, now which one do we take that as VC? Which is going to be the minimum of VCR and VC naught. So, that means you are going to calculate these both capacities at different sections. Whichever is going to be the minimum value, that you are going to consider that as the concrete shear resistance. Now, to meet the additional demand, then you have to put some extra stirrups, right. Okay. The resistance from stirrups, again we have already derived that as 0.87 Fy into ASV into D by SV, where D by SV is nothing but number of stirrups that are being crossed by the 45-degree crack, right. So, when do you provide minimum shear reinforcement? So, the code says that when your demand is between VC and 50% of the VC, that means my shear demand is less than VC, but it is higher than 50% of the VC. That means, again when concrete fails in shear, again it is a brittle mode of failure compared to that of when it is failing in flexure. So, the code wants to put some nominal minimum shear reinforcement to ensure that it is not going to fail in a brittle mode. So, this is the minimum stirrup, okay. So, you see here roughly if you look at it, area of AV by BSV is 0.4 by 0.87 into Fy, right. So, if you take Fy equal to 500 megapascal, just for comparison, but in our calculations typically IS code does not allow you to take Fy more than 415. So, if you take it, you get roughly about, you can put some 500 and then, if you do that, so basically it will become 0.4 by let us say 500. So, basically what is it you get? So, you get 0.2, 0.02. So, if you multiply it roughly it is working out to be, so basically 0.004 divided by 5. So, again that works out to be 0.00008. That when you multiply by 100 in percentage, you will see that it is working out to be 0.08, or roughly we can say it is about 0.1%. So, you can say roughly we need to put at least 0.1% of stirrup as the minimum stirrup reinforcement, okay. So, this is how we get 0.1% roughly, simple calculations, right, if you put it 0.1%. Now, there is also spacing requirement. The spacing of the stirrup also has to be less than this 2.175 times Fy into ASV by B. Now, you cannot put that means indirectly what the code is saying is, you limit the spacing so that you will have adequate number of stirrups that will be actually crossing that crack to make sure that the crack is not going to widen, okay. Then another one also, we should make sure that the spacing of the stirrup should be less than 4 times the width of the web or 0.75 times the dt, whichever is lesser, right. So, that is what we are saying. So, this is one requirement from minimum shear. Now, when the shear demand becomes more than 1.8 times VC, that means your shear demand is 80% higher than your concrete capacity in shear. Now, the stirrup spacing SV has to be further restricted to 0.5 times dt. That means, now you are relying more on the stirrup. So, the code is again wants to ensure that the spacing is kept minimum, so that it is not going to let the crack to open up very quickly and lead to brittle mode of failure, right. Again, the lateral spacing across the legs also, between, if you put multiple legs, again between that spacing between the legs, I cannot have spacing less than 0.75 times dt. So, these are all the spacing requirements from stirrup point of view. Okay, let us look at the design procedure now. So, we have first what that we do, we do the structural analysis and we draw the shear force diagram and bending moment diagram. and then we check the adequacy of the section. How do we check the adequacy of the section? We have to make sure that for bending first we design, and then we need to ensure that the tau v is again less than tau c max, right. That is the adequacy. Then we plot m naught on the bending moment diagram. Now, what is m naught? M naught is a decompression moment. Okay. So, m naught is your decompression moment. That means how much moment I need to apply to remove the pre-stress. Let us say I have applied a 5 megapascal in compression pre-stress. I apply external moment in such a way that that 5 compression becomes 0, right. So, that is what the decompression moment is, right. And then depending upon the cable profile, your m naught also is going to vary along the span if the tendon profile is not straight. Then we are going to check whether m is greater than or not m naught. Here so though it is a decompression moment, the code is saying that if the external moment, bending moment, if it is going more than m naught, we say that it is a cracked section, or if it is less than m naught, we assume that to be uncracked. Once we do that, then for each section you calculate VC naught and VCR. Now, again what is VC naught? It is a web shear capacity. What is VCR? It is a flexure shear capacity, right. So, then we determine the ultimate shear resistance as this. So, for uncracked region it is going to be VC naught plus P sin alpha. For cracked region VCR plus VC naught plus P sin alpha, right. So, this way. Then we design the shear reinforcement. If V is less than 50% of VC, that means the demand is less than 50% of what concrete can offer. You do not really need to put any shear reinforcement. Then if it is between the demand is between 50% of concrete capacity and full concrete capacity, we are going to provide reinforcement as per the class 23.431, and if your shear demand is more than VC, of course, we need to provide stirrups as per class 23.432.